Hello everyone, welcome to the 11th interaction session of network analysis. I'm your TA Dibanita. So for this week, Sir had covered the operational amplifier, its basic principles, and how like a open loop or a closed loop gain operation amplifier works. That has been taught in this week. So we'll be solving a couple of problems based on that. In so first, let us look at what is like how a operational amplifier works. So let's start off with how the operational amplifier works. The operational amplifier is denoted by a kind of a triangle like this, where there are two of the input terminals. One is called the non-inverting, so it is called the inverting terminal, denoted by a negative sign, and this is the non-inverting terminal, and it is denoted by a positive sign. Certain voltage V1 and V2 is given, and we get an output voltage VO. Now, whatever the voltage is across this loop, across these two terminals, the negative and the positive terminal, the output voltage is denoted by a gain factor times V2 minus V1, that is A into whatever the voltage is at the non-inverting terminal minus the voltage at the inverting terminal. Now for an ideal op-amp, this A is very high. That is, it is assumed that A almost tends to infinity. So this there are two other terminals in which the supply voltage may be given. So this is plus VTC and this is minus VDC. This can be further properly represented as this circuit. So there is an input resistance, a resistance or impedance, whatever you say.
Excuse me, ma'am.
Yes.
You are not audible.
Oh, I did not unmute, right? Sorry. Okay. Uh, I'm audible now, right?
Yes, ma'am.
Okay. So I was talking about this operational amplifier, which has one inverting, like two inputs. One is called the inverting terminal, the other is called the non-inverting terminal. The non one is denoted by this positive sign, and there is this output terminal. And this VDC plus VDC minus VDC are the supply voltage that is applied. Now, the output voltage V0 is denoted by the inverting and non difference between the inverting and non-inverting terminal voltage, and it is multiplied by a certain gain A, which is very high value in case of this ideal op amp. So the input of the circuit is denoted somewhat like this, where this is the input resistance, this is the V1 and this is the V2, which are the inverting and non-inverting terminal. So, and the output of the circuit is somewhat denoted by like this. So this is A into V positive, or in this case V2 minus V1. So, so if you imagine the actual op-amp circuit is kind of like this. So sorry for the diagram, it is somewhat like this, in which there is a resistance Rin at the input, but this resistance is considered to be very high. That is, Rin also tends to infinity. Now, from here we have the value of V0, right? V naught is equal to A into V2 minus V1. So um, in for this case, if I just simply assume that A tends to infinity, I'll write A in terms of V naught by V2 minus V1. This is the same thing. Now in an ideal op-amp, A almost tends to infinity. That is V naught by V2 minus V1 will almost tends to infinity. That is V2 minus V1 by V naught will tend to 0. So if we have this condition, then V2 will be equal to V1. So basically whatever the voltage is across this inverting terminal will be equal to the voltage across this non-inverting terminal. So in case of ideal op-amp, we get this condition that V1 will almost be equal to V2. And we if this resistance Rin is very high, that means whatever the current here will flow will almost will be a very small amount, because V1 will be almost equal to V2. So whatever the I will be, it will be V2 minus V1 minus of V2 minus V1 by Rin. If this is almost like a very high value, and we know this almost is equal to 0, because this is the condition that we get, this is almost equal to 0, that means the current drawn in this circuit will also be equal to 0. So whenever we will be solving any of the op-amp circuit, and if it is an ideal op-amp, we will assume that there is no current getting drawn into the input of the circuit, and the output of the circuit, this is for a this condition is just open loop, because there is no feedback connected to the input. So right now this whatever the output voltage will be, gain times V2 minus V1. This won't be exactly equal to 0, like V2 minus V1, it will be almost similar value. But for ideal op-amp, for our convenience, we will consider V1 is equal to V2 and there is no current getting drawn into the circuit. Okay. So the next thing you need to you must have seen in the lecture, sir has plotted the uh, diagram of V2 minus V1 in the y-axis it is the output voltage V naught. So in case of ideal op-amp, the if I'll just take another color. In case of non-ideal op-amp, there is a linear region beyond a certain difference of V2 minus V1. In this is case of a non-ideal one, when there is a voltage difference between the V1 and V2. So it will saturate and be equal to the supply voltage, which is equal to VDC, and beyond this a certain point this will go to minus of VDC. This is the supply voltage that is given. So the part from A to B, this is the non-linear region. In this region the op-amp will act as a linear circuit. So whatever the problems that we will be solving today is up to this region, okay, like not in the saturation region, because you will see most of the values of V naught that we will get will lie between the VDC and minus VTC. While solving the circuit, suppose we get a V naught value which is either greater than VDC or a V naught value which is less than minus of VDC, then the value of V naught will be directly equal to the supply voltage, which is equal to VDC. But if the condition is this, then whatever the V naught value will get, that will be equal to the answer. Now mostly what we will be solving is most of the circuits that we'll be solving will have a feedback, that is the output of the circuit will be somehow connected to the input with a resistance, capacitance, or whatever it may be. So if this is V1, this is V2, this is the inverting, this is the non-inverting terminal, this is V naught, the output terminal. So it will be somewhat connected to the inputs. For example, it will be connected by a resistor R1. Suppose there is another resistor, let this be R2. there another resistor be connected to the input terminal R1. And we have to like assume this is an ideal op-amp, that is no current is getting drawn into this circuit. So current in this branch, like from this node to this point, will be equal to 0. And if this particular value V2 has a certain voltage source connected, it will be that value V2. Or if it is connected directly to the ground, in case of instead of being connected to a voltage source, it may also happen that this will be directly shorted to the ground, then this will be equal to 0, and we will assume the voltage at this point A and this point B to be same, because this is an ideal op-amp. So this is how we'll be going forward with all the circuits. Now, like just to reiterate, like for example, if this was a non-ideal case, if this was the condition, so let's say this is V1, this is V2, negative, positive, this is V0, so R2, let this be equal to R1. So suppose there was certain voltage VA and certain voltage VB connected, if this is not a non-ideal case, then VA, VB minus VA times of whatever the gain will be the circuit will be equal to V0. That is, VB minus VA is equal to V0 by A. Now, suppose for example, like just considering that this gain value is very high, it is very high, then this particular value will be again a very small value, which will almost tend to 0. If you if you just assume this. So if in our tutorial we won't find a condition of non-ideal case, but if there is a non-ideal case, we will have to calculate V0 based on if the op-amp is non-ideal, this gain value either shall be given, or there will be conditions where we will be able to find this VA and VB. Like this thing you have to remember. Otherwise, in case of ideal case, again here if you see, like VB minus VA is equal to V0 by A, and this quantity can be ignored because if A is very high, this will almost tend to 0, where VA will be equal to VB, and again this current that will be flowing in this branch will almost be negligible and can be ignored. I hope like you are clear about this two conditions in case of ideal op-amp, because all the problems that we will solve will actually depend on will actually use these two conditions only. So shall we move to solving a problem?
Yes, ma'am.
Okay. So the first problem that we have here today is certain voltage is connected to the to the inverting terminal with R1, and there is a feedback loop where there is another voltage V2 along with resistance R2 that is connected, and the non-inverting terminal is connected to the ground. So this circuit we will consider, like all the circuits that we will solve will consider to be ideal op-amp. Okay, so first we can calculate the voltage that is at this particular port. This is suppose VB, this is VA. So we have VB is equal to 0 because it is shorted, like it is connected to the ground. So this voltage will be equal to 0 volt, right? Now in case of ideal op-amp, VA will have to be equal to VB, and the current that will be drawn inside the amplifier will be equal to 0 ampere. These are the two conditions of ideal op-amp. So we have VA equal to VB, and this will again be equal to 0 volt. So the node voltage at this point is 0. So let this point be denoted by A. Now what, in order to solve V0, V0 is the node voltage here. So in order to solve the value of V0, we can apply KCL at A. If we apply KCL at A, then whatever the current that is flowing here, because no current is flowing into the OPAMP, all this current will actually flow in this particular branch, right? So it will be V1 minus the node voltage at A, which is equal to 0, by the resistance R1 will be equal to, so whatever the current is flowing out of the circuit, right? So it will be, so we will encounter with V2 first. So it will be V2 minus this node voltage V0 by R2. Current flowing in is equal to current flowing out, right? So we have all the values of V1, V2, R1 and R2. So we can compute V0. So let us compute V0. So V1 is 4 by R1 is 4 kilo ohm. V2 is given as 2 volt. We do not know V0, and R2 is given as 4 kilo ohm again. So these two can be cancelled. So V0 will come out to be 2 volt. Now look at the supply voltage. V supply is 15 volt given. So whatever the V0 that we got is less than 15 volt and greater than this minus 15 volt. These are the supply voltage, right? So this, whatever the voltage we obtain V0 actually lies between the supply voltage. Hence, for now our region is this particular region, which is very steep. Like as the gain increases, the ideal OPAMP almost looks kind of like this. But for now, I'll just draw it. It is in the linear mode now, not in the saturation mode. Right? If it was saturation, then V0 would have been greater than this 15 volt. Please remember that. Just the reason why this supply voltage is given, just to check this condition whether we should write like is the answer 2 volt or something else. Suppose we have gotten like 16 volt, then the answer would have been 15 volt, because the saturation takes place at whatever the V supply will be, minus plus VTC and minus VDC in this case. So if we had gotten 16 volt as V0, suppose this was not the condition, like in some random other condition, if we had gotten V0 equal to 16 volt, our answer would have been the supply voltage, that is 15 volt. If V0 would have been suppose minus 16 volt, then we would have written the answer as minus 15 volt, which is the supply voltage. Is this clear?
Yes, ma'am.
Okay. Any
Ma'am,
questions? Yes?
V0 is equals to minus 2 volt, na?
Uh, is it minus 2 volt? Did I
Yes,
write
ma'am.
something
Yes,
wrong in
ma'am,
PCM?
-2.
So, yeah. Okay, this is minus V0, right? Okay, right. So V0 will be equal to 2 minus 4, which is equal to minus 2 volt. Thank you. Yeah. And anything else?
No, ma'am.
Okay. Then let's, like, all the questions of the operational amplifier will be like just pretty much simple, only the circuit will change. So you, and one thing to note that, like, all the all this feedback gain which will like that will be given into the circuit, the closed loop gain, it will always be connected to the inverting, like this inverting terminal. In each circuit you will see this gains. For example, now here this feedback loop is connected to the inverting terminal of the circuit. It is always connected in that way. Okay, now for this circuit, voltage and a resistance are two voltage and resistance are connected across the inverting terminal, and the feedback gain is given, like feedback loop is connected by resistance R3, and this is VB in this case, because the positive terminal, it is the non-inverting terminal, it is connected to the ground, which is at 0 volt. So in case of operational amplifier, the voltage across here is equal to the voltage across here, so this is also 0 volt, right? and no current here, I equal to 0, because no current is getting drawn inside the amplifier. So whatever the current will be here, I1, and whatever the current flowing here will be I2, will all come and flow in this particular, this will be I1 plus I2, because no current is getting drawn into the amplifier. Right. Okay. So this node voltage will be equal to 0. So this node voltage will be equal to 0 volt. So let this be A. So if I again apply KCL at A, so it will be whatever the current I1, so let this be equal to I3. So using KCL, I1 plus I2 will be equal to I3. So what is I1? I1 is V1 minus 0 by R1. I2 is, so V2 minus 0 by R2. This will be equal to I3. I3 is equal to 0 minus V naught. This node voltage is V naught by R3. So, like, yeah, is this correct?
Yes, ma'am.
Okay. Now you have all the values of V1, V2, and R1, R2, R3, right? Can you calculate V naught? Please calculate V naught. Are you getting the value of V naught to be
Yes,
minus?
ma'am.
Right. Now this is between the supply voltage, right? This 1.1667 is between 15 and minus 15. So the output voltage will be minus 1.1667. Is this fine?
Yes, ma'am.
Okay. If there are no questions, then we'll move to the next one. So, like, since I have shown two problems, like based on ideal OPAMP, can you like intuitively tell, like, for this case what we will do? So this is again a feedback loop from V naught is connected in a certain fashion to the non-inverting, to the inverting terminal, and the non-inverting terminal is connected to a voltage V1. So the voltage at this point VB will be equal to
V1.
V1.
VB will be equal to V1, and what will be VA?
Same VA. V1. It
Right.
is.
Whatever the voltage will be in here will also be the voltage in here. So it is V1. So again, like right now we will apply KCL at this particular point. So can you tell me the equation? What will be the equation? So what will be the voltage VA? First we will, if I find the node voltage here, then I can relate to V naught, and here it is ground, so here it is 0, right? So VA will be equal to, can anyone tell me what will be the node voltage at VA?
VB minus VA, V1.
Right. It will be, come again?
VB minus V1.
Uh, VB.
VA plus
Minus.
V2 minus V1.
So at this node it is V1, right? So it will be V1 minus this particular voltage V2, right? Will be the node voltage at this
Yes,
point,
ma'am.
right? So VA will be equal to V1 minus V2. Now we can apply KCL at A. So you see, like, there will be no current that is getting drawn into the OPAMP circuit. So the current in this particular branch is 0, right? Because there is no current getting drawn into the input of the OPAMP. So whatever the current will be in this particular branch will be the current, like the same current will flow from like V0 to through R1 and R2 to ground, right? So I1 will be equal to, I1 plus I2 will be equal to 0. So what is I1? I1 is the node voltage at V1, VA minus V0 by R1, and I2 will be equal to VA minus 0 by R2. This will be the KCL equation. So we have already got VA. VA is V1 minus V2 minus V0 by R1 plus V1 minus V2 by R2 will be equal to 0. Now we have all the V1 and V2, and we can simply plug in these values and calculate V0, right? So please calculate V0.
Ma'am, is it 1 by 2?
No, it's supposed to be 3 volt. R1 is 5 kilo ohm. Let me check. Like, so this will be equal to 2 minus V0 plus, yeah, so V0 comes out to be 3, right? So from here I'm taking 5 into 10 cube common. So it will be 2 minus V0 plus 3 minus 1 is 2 by 2 into 1 by 5 into 10 cube. So I'm equating this to 0. So now this comes out to be 1. So V0 is 3 volt, right?
Yes, ma'am.
Yeah. Okay. So I mean, all for all the circuits that you'll be solving, just look at the condition and then apply KCL to calculate whatever the question has asked. Mostly in all of the question you'll find like what is V0 is the question. So like in this case you see supply volt is around 12 volt, which is in between minus 12 and plus 12. The answer that we got is 3 volt. Okay, so let's move on to the next question. So yeah, okay. So in this case, the input of the this two input amplifier, you see, like it is connected in a fashion with different resistance in such a way that the input and output port are not really, like, you know, independently connected to certain voltage, but there will be certain voltage across this node here and here, and the inverting terminal is connected to the output V0 with R4. So now you have to calculate V0, right? So one thing that we know here is whatever the voltage here VA will be equal to the voltage here VB, VA equal to VB, and there is no current getting drawn in this, or there is no current here in here, right? So I'll just write this node voltage as VA, and this node voltage, since it is connected to VB and VB equal to VA, I will also write as VA, right? What will be the node voltage here? Anyone?
V2.
This, yes, because it is connected to this V2, which is again grounded. So this voltage is V2. So whatever the current will start flowing here will not flow into this OPAMP and will flow in this particular branch, right? And whatever the current is actually flowing either maybe from the output or to the output is not going into the OPAMP and flowing like this, right? Is this okay?
Yes, ma'am.
Okay. Now we will apply like KCL either like in this node or in this node. Let's see. Like let's apply KCL once at this node and second time at this node, right? So I'll write KCL at, suppose, plus end. That is in here I'm applying KCL. So it is V1 minus VA, right, by R1 will be equal to VA minus, this is V2, by R2. This is one KCL equation we have. The second KCL equation we'll have is from the negative terminal, like in this particular point, right? So if I apply KCL at that particular point, so it is whatever the current is coming, that is V0 minus VA by R4 will be equal to VA minus V2 by R3. Is this fine?
Yes, ma'am.
Yeah. Now you have two equations and the unknown here is V0 and VA. So two equations, two unknown, we'll be able to solve it. So please let me know like what is the value of V0 you are getting. So
Excuse me,
yes.
madam, you are muted. Uh, I think you are muted.
Okay. So I just asked you to calculate like the V naught. So we have written the two KCL equations, right? This first equation at like this terminal, which is the positive terminal, and the second equation, which is at this particular node, right? This
Ma'am,
first node and
it's
second node.
115, no?
Sorry?
It's 115 minus 70, I guess.
Yeah, yeah. Sorry, 115, right? Yes. So it is 45 by 21. So this comes out to be, let me get the calculator. 45 divided by 20. 2.1428. So from the first equation, the only unknown that we have is VA. So rest of the parameters we have in the question. So we put it and get that voltage VA is equal to 23 by 7 volt. And in the second equation, we have two unknowns, V naught and VA. So we plug in the value of VA here, and V2 we have, R2 and R3 and R4 we have. So we put in all the values and we calculate V naught. V naught comes out to be 2.1428 volt. Clear? If we, any question on this one?
No, ma'am.
Okay, then let's move to the next question. So this is again a very straightforward question, right? So this is the voltage VA, this is VB. So VA is equal to VB and VB is equal to, what is the
VB is
value?
equals to V2.
Right,
4 volts.
4 volt. So this node voltage is 4 volt. Now you will apply KCL at this particular point A and you'll be able to figure out V naught, right? So this is V1 minus VA.
Ma'am, we'll get 0, ma'am. Is it okay?
Sorry?
V1 minus VA, we are getting 0.
Okay, like you have to figure out V naught. Calculate V naught. So it will be equal to VA minus V naught by R2. So calculate V naught. That is the aim that you have. So did you get the value of V naught?
4 volts, no?
Right. R1 is 2 kilo ohm. This comes out to be V is 4 minus V naught by R2 is 4 kilo ohm. So 4 minus V naught by 4 into 10 cube equal to 0. So V naught will be equal to 0. This kind, 4. This kind of circuit, like where the input voltages are both 4 volts and the output that we get here is also 4 volt. This is kind of called the unity gain. Please note that, like, suppose we had a circuit somewhat like this. So whatever the voltage we had here would have been, suppose we had applied plus 4 voltage here, plus 4 voltage here. So these two, nothing is connected into the circuit. So this is 4 volt, this is 4 volt by definition, and since there is nothing connected here, we will get a 4 volt here. So this is actually no resistance or anything is connected. So this is a unity feedback loop, right? So we would have gotten a, so although in this case the two voltages may, or like in this case it is same and there is certain resistances connected across it, but we end up with getting the output voltage to be 4 volt. So basically this particular circuit is a unity unity gain feedback, like closed loop circuit. Okay, so let's move to the next question. So in this case again, like this particular voltage is V1, so we will get V1 here. So what will be the node voltage here? What will be the node voltage here?
4 volts.
Sorry?
4. 4.
Yes, will be equal to V1 or 4 volts. Now you can apply KCL at this point A. Please tell me the equation.
4 minus 6 by R2 is
Yes,
equals to VO minus 4 by R1.
right. So for now I'll just write it in terms of V1. So V naught minus V1 by R1, which is the current here, will be equal to V1 minus V2, and this is 0 by R2. So please quickly calculate V naught. You're getting 3 volts, right?
Yes, ma'am.
Okay. Then we'll try another circuit which is similar to the previous circuit. Only difference is instead of any voltage, instead of any resistance, a voltage V2 is connected between, like the end of the inverting terminal and the output voltage, right? In this case too, this is V1, so this will be also equal to V1, that is, this is V1, right? Now you have to calculate V naught. So whatever the current that is flowing out of here will come and flow in this circuit, because there is no current in this case in here. So we will just write one equation.
Is it 8 volts, ma'am?
Sorry?
V naught is equals to 8.
Right. V naught is equal to 8. So it is V naught minus V2 minus 0 by R. This will be equal to 0, right? So V naught will be equal to V2. Sorry, did I miss something? Oh yeah, minus V1, I forgot. So V naught minus V2 minus V1 minus 0 by R. So V1 will be equal to V1 plus V2, and this is 4, this is 4, this will be equal to 8 volt. So what kind of circuit are called, like which kind of circuit does this imply? So had we, imagine if we had like kind of a, this two voltage V1 and V2 are getting added up, but since V2 is connected somewhat related to the feedback loop of the network, so we end up with 8 volt. Imagine if V1 and V2 are the input voltages, so they are getting added up and we are getting V0 is equal to 8 volt, which is equal to V1 plus V2. So this is kind of a adder circuit, but actually this is not a straightforward adder circuit. This V2 input voltage is connected in form of a feedback. It is replicating an adder circuit. So like whichever the configuration the circuit is connected in, the amplifier, like it's not necessary that the adder circuit that sir had shown, if you remember, like there were two input terminals which is again connected to the inverting terminal of the input, and like that is how the adder circuit was shown. Like this is just to show like there might be different configuration in the circuits. So can we move to the next one? So can you please try this particular circuit and calculate V naught?
Ma'am, excuse me.
Yes.
In previous question, uh, uh, while applying KCL at V1,
KCL at V1. Okay.
you have applied KCL at V1, na, ma'am?
Sorry.
How this equation we have written
Okay.
KCL or something else at V1.
So I mean the thing is you can write KCL at V1, but there is no like resistance connected here, no. So it's
Okay.
like just the voltage that we get at this particular node, and then we write the equation. So whatever the current that will flow out of the circuit will only flow but through this branch, because there is no current flowing across this particular branch.
Yeah, previous to this, ma'am, please show
Sorry.
previous to this question.
Yeah,
Uh,
there like we could
Here we can write KCL at node A.
see, you can either write KCL at this particular node A or just write a equation of loop from here to here, right?
Okay.
I mean, here resistance was connected here, so we could have like we independently wrote the KCL equation. Instead of that, like from V0 to ground, see all these voltages are connected to the ground. V1, V2, and everything are with respect to the ground. So we can write just one single equation which starts from this particular point and ends here, and we will get back this equation only,
Okay, ma'am. Got it.
right? So yeah. So this eighth question, uh, so again the same condition, this is V1, so this is also V1, so this particular node voltage is V1. Now how do we solve this? Where do we apply the KCL? I mean, you can either
Everywhere.
apply KCL or the uh, like loop equation. Where will we apply the KCL?
V naught.
Here?
V naught, ma'am. Yes. At V naught. V.
At this particular point, are you suggesting?
Yes, yes, yes. Yes, ma'am.
So do we know the current from here?
No, that current we do not.
We do not know, right? So instead of that, we will just apply
Mom,
KCL.
KCL at V1, mom.
Sorry? Yeah, KCL at V1 would be an ideal option because we know the node voltage here, V naught. So let's apply KCL at V1 because we know like whatever the current like will be flowing from this particular branch will flow through this branch because there is no current flowing through this particular branch, right? So the best option would be to relate V not with the input parameters that are given is applying KCL at V1. So this is,
Mom, again it's 8. Mom.
sorry, 8. Okay,
V naught is equals to 8.
right, it could be. So V naught by V1 by R1 will be equal to V1 minus 0 by R2. So V naught minus V1 is 4, R1 is 5, V1 is again 4, R2 is 5 10 cube. So this will get cancelled, V naught will be equal to 8. 8 volt. So just like this is a small thing that you have to remember, like do not apply KCL here because you do not know. For that you need to know the current that will be in this particular branch. Then only you will be able to calculate the current that is flowing in this two particular branch and calculate it. So apply KCL at V1. Then let's look, if this is done, then we'll move to another problem. So let's look at this particular problem. Here both the the inverting and non-inverting terminal has resistances connected across it along with a voltage source. So I'll just assign voltages here and here. So this if this is VA, this also has to be VA. So we know the node voltage here, VA, and we have to calculate V naught, right? So in this case, how many KCL equation we will get? How many KCL equations shall we write here?
2.
2, right? One we will write at this particular node, and this next one we will write at this particular node B. So whatever the current that is flowing here will flow in this fashion, as current here will be equal to 0. So V1 minus VA by R1 will be equal to VA minus 0 by R2. This is KCL at A. Then the next KCL we will apply at B, and we will get V2 minus VA, because whatever the current will flow in this branch will go like this. So V2 minus VA by R3 will be equal to VA minus V0 by R4. So solving this two equation, we have two unknowns, one is VA and the other one is V0. So we'll be able to just substitute the value we get from the first equation of VA, we will substitute it in equation 2 and solve V0, right? So please quickly solve it. V1 is 2 volt, VA we do not know, R1 is 3 kilo ohm, VA by R2 is 2 kilo ohm. So we get 4 minus 2 VA equal to 3 VA. So VA is equal to 4 by 5 volt. So let's substitute in equation 2. V2 is 1, VA is 4 by 5. This is R3. R3 is 1 kilo ohm. VA is again 4 by 5 minus V0, and R4 is 2 kilo ohm. So this is 1 by 5. 2 from this side I am bringing in on top. 4 by 5 minus V0. So V0 will be equal to 2 by 5 plus 4 by 5. 6 by 5 volt.
Excuse me, ma'am.
Yes?
V naught will be equal to 4 by 5 minus 2.
Yeah, yeah. So yeah, this one I'm bringing in this side. So it is minus 2 by 5. So 2 minus 4, it will be 2 by 5. Right? So this is 0.4 volt. Everyone getting 0.4 volt?
Yes, ma'am.
Okay. So yeah, let's move to the previous assignment, like which was rolled out. This one was the last question, and then we'll solve a couple of questions that are from different sources. So in this case, like the non-inverting terminal is connected with a resistance and a voltage source, and the inverting terminal is connected to the output, directly to the output. So you will have to calculate V naught. So what will be the voltage at this point, VA? What will be VA? Just apply the OPAMP, like ideal OPAMP condition.
Will be VO. V naught.
Yes, because this is directly
V naught.
this is directly connected to the output. So this is V naught. So this is also equal to V naught. So whatever the current will flow in here will also flow here, and this will be the loop because no current is flowing here. So we have one single equation. Like you can either apply KCL at A or just write the loop equation, up to you. So it will be V1 minus V naught by R1 equal to V naught minus V2 by R2. Now you can solve for V naught. V1 is 4 volt, V naught is unknown, R1 is 4 kilo ohm, V2 is 2 and R2 is 4. R2 is also 4 kilo ohm.
Is it 3?
2 V naught equal to 6. Yes, V naught is equal to 3 volt. Right? So these were the ones that was like questions from the previously rolled out assignment. So I would assume like whatever you have in this assignment will be similar to this kind of questions. Now, like we'll be solving 4 or 5 questions that are from different sources, just to, in case like any other current or voltage, branch current or voltage may also be asked into the circuit, and however way the circuit may be drawn, just remember to apply the same conditions of ideal op-amp and you'll be able to figure out the output voltage or any other current. So in this case, if you consider this particular amplifier which is shown here, you see like usually the output terminal is connected, is shown like this, right? But that output terminal is also with respect to the ground. So whatever the circuit that we see here, like in this case this V naught is actually the output voltage. Like if I consider this is V naught, right? So it is similar to the previous questions that we have. Only thing is this connection is shown in a proper way. Like earlier we had like connections like this. So this thing connected and this was connected to the ground. This is exactly the same thing. In this case, like suppose 2 volt, this is 5 kilo ohm, and then this is 2.5 kilo ohm, and this is the 1 volt source which is again connected to the ground. And this is connected to the inverting terminal, and the non-inverting terminal is connected to the ground. This is this is connected in this way to the ground actually. So this is 2 kilo ohm, this is V naught, and this is connected in this fashion with 10 kilo ohm. So you see these two circuits are exactly the same, only the way it is drawn is with respect to ground. Like all of the elements are drawn like with respect to connection with the ground. So this circuit is actually same as this particular circuit. So in the question it is asked, you have to calculate V naught and I naught. So can you tell me how you will go about solving this? So
KCL.
yeah, of course KCL. Like first of all, the voltage in A and B will be equal. So let us just, so can you tell me the voltages at VA and VB? What is VA and VB?
It will be minus PU.
No, look, the voltage drop across this resistor is V0, but this particular point is connected to the ground, right?
Zero is zero.
Yes. So this will be equal to 0 volt. So this will be also 0 volt. So now you can apply
Ma'am, is V not 4?
V0. What is the,
4.
just let me check. No, it's -8. So at which point will you apply KCL?
VA, ma'am.
Right. Because that will be related to the output port, which is V0, and we have the input voltages and resistances. So this will be equal to whatever the current will flow in this branch and this branch will be equal to I1 plus I2, whatever the current that will flow in this particular branch if we apply KCL at this point. So it will be 2 minus 0 by 5k plus 2 point, 1 minus 0 by 2.5k will be equal to 0 minus V0 by 10k. So I'm just writing in k, this is 10 to the power 3. So it is 2 by 5 plus, if I just remove the point, it is 10 by 25 will be equal to minus V0 by 10. So 25 is the LCM. So this is 10 plus 10 minus V0 by 10. V0 will be equal to minus 20 by 25 into 10. So it is minus 8 volt, right? Are you getting this?
Yes, ma'am.
Okay. Now can we calculate
Yes,
I
ma'am.
naught?
-8.
Yeah. So can we calculate I naught now? How will we calculate I naught?
By using KCL at node V0.
-8 by 2K.
Sorry?
Ma'am, we have KCL at V naught, ma'am.
Right. So when we apply KCL at V naught, what will be the value of I naught? I naught equal to, in terms of equation,
V naught by 10K plus V naught by 2K.
right. So it will be equal to the current that is flowing in this particular branch and this particular branch. So we have the value of V naught, so we can calculate I naught. So I'll just remove the k and write in terms of milliampere. In the denominator it is 10 to the power 3. If I bring it to the numerator, it is 10 to the power minus 3. So it will be in milliampere. V naught is equal to minus 8, and this is 1 by 10 plus 1 by 2. And this will be 1 plus 5 minus 24 by 5 milliampere. So this comes out to be 4.8 milliampere. So actually the current direction is in this direction, right? So this is how you will, like, no matter in which way the circuit is given, as the conditions are same, you'll be able to figure out under any conditions, right? So let us do one problem. Like in sir's lecture, sir has told about like this may not be a resistance, this could be an impedance, like that are connected. So let us do solve a simple problem where a capacitor is connected through the output of the terminal to the inverting uh, inverting input of the OPAMP, right? So no matter what is connected, like whichever element may be connected at the input or output, we will just apply the OPAMP conditions and KCL to solve it, right? So let this be VA. So VA will be equal to, what will be VA?
0
0.
volt, madam.
Right. Since this is connected to the ground, this is 0. Now we apply KCL at VA. So can you tell me the KCL equations in this case? So current
It will
here,
be V1 minus VA by 3 into 10 to the power 6
huh,
plus V2 minus VA, that is 0, and divided by 100 into 10 to the power 6
will be
is
equal
equal
to,
to VA minus 0 minus 0 upon and in terms of S we can write it.
yeah, we can write it in S, but like then we have to convert all this in S. So you can also write in terms of the differential equation. Like since this is a
Minus
simple
1 by
problem.
C.
So how is the current equation written? C dV by dt, right?
Yes,
Minus 1 by C into integral of I into dt.
So we are writing the current equation, right? Not the voltage equation. So what you are saying is voltage is 1 by C integration I dt. But we are actually writing the current equation. So we have to write C dV by dt, right?
Yes, ma'am.
Yeah. So the voltage across this capacitor will be like if I write this as the positive and this as the negative terminal, this is minus V naught, right?
yes,
So instead, so we will write C dV by dt. So in this case, it will be, since it is minus V naught, so it is minus C dV naught by dt. Is this fine?
yes,
Yeah.
Yes, ma'am.
And we have the value of V1 and V2 in terms of like t in this equation, and it is given like uh, we have to find V of t at t greater than 0, and before 0 the capacitor did not have any voltage across it, so the initial conditions are 0. So now to find V naught we will have to like simplify this and just integrate it, right? So let us put V1 is so yeah, I'll take dv naught by dt in this, in the left hand side, and rest I'm putting in the right hand side. So C will go to be minus 1 by C, right? So in this case here minus 1 by C. C is given as 2 microfarad. So 2 into 10 to the power minus 6 times V1 by 3 into 10 to the power 6. V1 is 10 cos of 2t. So 10 cos of 2t by 3 into 10 to the power 6. I've taken the negative sign outside, okay? Then it is again 1 by C, so it is 1 by 2 into 10 to the power 6 times V2 is given as 0.5 T, and R2 is 100 into 10 cube is 10 to the power 5. So I'll just simplify this side, so it will be minus, so 3, so 10 to the power 6 and 10 to the power 6 will get cancelled, so it will be 10 by 6 or 5 by 3. 5/3 cos of 2t plus, so 10 to the power 5, we will have 1 10 to the power minus 1 here, so if we bring it up, it will be 5/2. 5/2 into t. So now from this equation, if I just write, so v naught will be integration of dv, right? So dt I am bringing it on the other side. So this will be equal to integration of, so negative I am bringing on the outside, 5/3 cos of 2t into dt minus integration of 5/2 t into dt. And what will be the limit of the integral? We are asked to find v naught t for t greater than 0. So it will start from 0 to t, right?
Yes, ma'am.
Yeah. So it is 5/3 integration of cos of 2t is sine of 2t by ddt of 2t, which is 2. And so it will be from 0 to t, and this is 5/2 constant will come out. Integration of t is t square by 2 from 0 to t. So it is minus 5/6 sine of 2t minus sine 0 0, so the other term will get like nullified, and this is 5/4 into t square. Since if I put 0 in place of t, this will go away and we'll get only 5/4 t square term. So just like if I write it in terms of like this fraction can be reduced, and this will be the value of v naught of t for t greater than 0. Now in the question, if it is asked like at a certain t you will have to find out, then you can just plug in the value of whichever particular time interval it is asking, and we can calculate this. Is this fine?
Yes.
Yes, ma'am.
Yeah. So let us do another problem in which this input voltage Vi is given by this particular waveform. So in the question it is asked to sketch the output waveform V naught in the circuit for the given input voltage waveform. So again, this is the output terminal V naught, which is connected with certain resistance, which is not actually mentioned here, but we wouldn't really need to use it to draw the output voltage waveform. We'll see it later. So again, like the ideal OPAMP condition will apply. So I here will be equal to 0. This is equal to 0 volt. So this will also be equal to 0 volt. The capacitive and the resistive voltage are given here. So let us just write first V naught in terms of Vi, and then we will draw the waveform. So we can apply KCL at this particular node A. So now that you have solved one question based on capacitor, can you tell me what will be the KCL equation? So whatever the current here will be flowing in this particular branch I, right? And this is 0 volt. So it will be current that is flowing through the resistor will be equal to the current flowing through the capacitor. So IC is
C dV dt.
right. So it is C dV by dt, and dV here is Vi minus,
VI.
and this is
VI.
0, so only Vi will be there, and IR will be 0 minus V naught by 5, like whatever the value of R will be. So we'll just plug in the value of R and take the negative sign this side. So we will write V naught in terms of minus RC into dVi by dt. This will be the output voltage equation, right? So let us just calculate RC because this is a constant. RC will be equal to uh, C is 0.2 microfarad and R is 5 kilo ohm. So this is 5 to the 10, it will get cancelled, so it will be 10 to the power minus 3. So this value is 10 to the power minus 3. So V naught will be equal to minus 10 to the power minus 3 dVi by dt. Now we will have to calculate like the conditions. So let us write Vi in equation form. So this is the waveform that is given. So if I am to write Vi in terms of t, in the form of an equation, what will it be? So let us do part by part. Like up, it is a like a periodic waveform. Like first we will write equation up to 0 to 2, then it will be 2 to 4, and this particular periodic fashion will continue, right? So V of I, we will write the condition from 0 to 2 volt and 2 to 4 volt, right? So between
Yes,
0
ma'am.
so between 0 to 2,
It is a straight line.
it is a straight line, right? And what is the slope?
4 by
So
2.
slope is 4 by 2. So if I write in terms of y equal to mx plus c, the intercept here is 0, right? It will be only 4 by 2 into x. In this case, x is t. In the x-axis, it is t. So this is equal to, now please note one more thing. This is in millisecond. So it is 4 by 2 to the power minus 3, right? Is it fine?
Yes.
4 into 2 to the power minus 3 into t. This is the condition when 0 to 2. And in the next case, what will be the condition?
Ma'am, why are we taking C as 0, ma'am?
Because this intercept is cut going through the origin, right? If I just consider this line, so this is 2. Suppose let's say this is 2 and this is 4. So this is the equation of the line, right? So there is no y-intercept of this line. It is passing through the origin, right? So equation of
Yes,
this
ma'am.
line is actually x equal to y. But since these two coordinates are not same, this is 4 and 2, the slope of the line will be different. So it will be, if I write y equal to mx plus c is the equation, here since it is passing through the origin, so y-intercept, there is no y-intercept, so it is 0. Slope is whatever the del y be, del y is 4 and del x is 2, but this is in millisecond. So this will be 2 into 10 to the power minus 3, right? To balance the unit. And here x is actually t. In the x-axis we have time. Is this fine?
Yes, ma'am.
Okay. Now for the interval of 2 to 4. So what will be the equation? I'll just draw the line like this. So in this case, you see this is 2, this is 4, there is a line like this. So can you tell me what will be the y-intercept here? The equation will be again y equal to mx plus c.
8, ma'am.
Right. This will extend and go and cut the y-axis at 8. So this will be 8. And what will be the slope?
8/4.
No. Like, okay, yeah, 8 by 4. Fine. So it will be 8 by 4 into 10 to the power minus 3 because this is millisecond. Right? So this is 2 by 10 to the power minus 3 or 2000. So this is, but please note that this slope is negative, right? This is minus,
Slope will be taken as negative.
sorry?
Slope will be taken as negative.
Yeah,
Minus.
slope is negative. So it is minus 2000 plus 8, minus 2000 t plus 8. So I'll just write the equation in a proper fashion in the next page. So let me just take the waveform because so if I write Vi, this is 4 by 2, so this is 2, and if I take 10 to the power 3 on top, it will be 2000. 2000 t, this is the condition between 0 to 2, and the condition between 2 to 4 will be minus 2000 t plus 8. So it is minus 2000 t plus 8. This is the condition of Vi. So I can also write V naught in the similar fashion. V naught is actually that we have like already calculated. It is 10 to the power minus 3 into dvi by dt. So it is 10 to the power minus 3 dvi by dt. So first multiply into 10 to the power minus 3 and do ddt, right? So minus 10 to the power minus 3 into dt of 2000 t. This is the condition from t to 0 to t, and then again like the same thing, minus 10 to the power minus 3 into ddt of minus 2000 t plus 8. This is the condition from 2 to 4. So we come up with, so if I multiply, it will be minus 2 ddt of t is 1. So it is minus 2 from 0 to t, and between 4 to 2, so 10 to the power minus 3 if I take in, it will get cancelled, minus minus it will be plus, so 2 into ddt of t is 1, and ddt of 8, since it is constant, it will be 0. So we get V naught as minus 2 and plus 2 between these two time interval. So what will be the waveform? How the waveform will be of V of V naught? So if I just take a different color, so between 0 to 2 it is minus 2 volt. So it is minus 2. And between 2 to 4 it is plus 2 volt. This is plus 2. So the waveform will look somewhat like this. And since this is periodic, this will go on. Is this clear?
Yes,
Yes.
ma'am.
Okay. Then, so in this case, there are two operational amplifiers instead of one. connected in a fashion as shown here, and you have to calculate the output voltage V0 and the branch current I0. So will you be able to do this? So for each of the operational amplifier, we'll apply the like ideal op-amp conditions. That is just just think that the output of this is actually connected to the non-inverting terminal of the second amplifier, right? So whatever the voltage will be here will be the voltage across here and will be the same voltage across here. So we see that this particular voltage is connected to 5 volt. So using ideal op-amp condition for the first amplifier, this will be equal to 5 volt, and using the since nothing is connected to it, this output is also equal to 5 volt. So the non-inverting terminal of the second amplifier is at 5 volt. So we can using the ideal op-amp condition for the second amplifier, this particular node voltage we can calculate to be 5 volt.
Ma'am, will it not be minus 5, ma'am?
Sorry, like which one are you
Okay, okay,
talking
got
about?
it, ma'am.
This is the positive one, right?
Got it, ma'am.
Yeah.
It was for non-inverting terminals, so yeah.
So yeah. So we have the node voltage across this 50 kilo ohm resistance and 200 kilo ohm resistance. Now we can apply KCL at this particular node A, right? And we can calculate V0, I0, whatever the question is asked. So just quickly apply it and find out V1 and V0 and I0. So 5 minus 0 by 50, I'll just write K means 10 to the power 3, and the current here is 5 minus V0 by 200K will be equal to 0. 5 by 5, I'm just removing 10 to the power 3, 5 minus V0 by 200. So this is 5 minus V0 by 200 will be equal to, so I'll take this one on the other side.
Ma'am, B naught is equals to 25.
Okay. This is 50, sorry. So minus 5 plus V0 equal to 20. V0 is equal to 25 volt. Right. And what will be the value of I0?
0.1 milliampere.
Okay. So I0 will be equal to 5 minus 0 by 50 into 10 to the power minus 3, which is 1 by 10 milliampere or 0.1 milliampere. Right. So let us do one last question and then finish it off. So can you calculate V0 and I0 for this particular circuit? By now you'll be able to do it, I'm pretty sure. I'll just give you 2-3 minutes to solve it, then I'll be solving it. This particular assignment is a very scoring one because it is a very straightforward questions. So everyone please do it properly. Just there are two things you have to do: apply the op-amp condition and apply KCL. So please do it properly. Let me know like when you are done with calculating V naught and I naught, right?
Ma'am, is it 3.8 volts?
Just hold on. With a negative sign, right?
Ah, yes, ma'am, minus.
Yeah. Yeah, right. And current is
Minus 0.95 milliampere.
it's little different than what I got. Okay. Uh, so I hope everyone has tried out. If yes, please let me know if you get any other values. Then I'll start solving. Please try to like everyone please try to solve this one circuit because like rest of the questions will be similar, like you just have to do the same thing again and again, so I just want you to try it out. Please let me know if anyone else got any other value of current and like voltage, output voltage and output
Ma'am,
current.
1.425.
Minus 1.1425 you mean, right?
Yes, ma'am, milliampere.
Yeah, yeah, you're right. Others, have you done it? Okay, I mean, since no one is responding, I'll start off then. So this particular of the like non-inverting terminal is connected to the ground, which is 0 volt. So the node voltage here is also 0. So now we can apply at this particular junction A, we can apply the KCL. So this node voltage is V naught. So we have 1.5 minus 0 by 20 kilo ohm plus 2 minus 0 by 10 kilo ohm plus 1.2 by 1.2 minus 0 by 6 kilo ohm. All this current in this particular branch will flow through this branch, right? So this will be equal to 0 minus V naught by 8 kilo ohm. Now all this 10 to the power minus 3 plus 3 I'm cancelling. So this is 1.5 by 20. So I'll just take the LCM. So this is, so LCM is 60. So this is minus V naught by 8. So this is 4.5 plus 12 plus 12, right? So V naught will be equal to minus 8 into, so this is 24, 28.5. So 15. So this is, if I just multiply it by 2, it will be 0. 57 by 15, right? So this will be equal to minus 3.8 volt. So V naught we have calculated to be minus 3.8 volt. Now what is I naught? I naught will be, if I even apply KCL at V naught, I naught will be the two current that are flowing in this particular branch and this particular branch. So I naught will be equal to V naught by 8 kilo ohm and V naught by 4 kilo ohm. And V naught is minus 3.8, right? So minus 3.8 into 10 to the power minus 10 to the power 3 will be equal to 1 by 8 plus 1 by 4. So I'll write it in terms of milliampere. So it is minus 3.8 into 3 by 8. So 3.8 into 3 divided by 8 is minus, so I naught is equal to minus 1.425 milliampere. So I hope everyone has done this. So this brings us to the end of all the problems for today. If anyone has any question, you can ask. Otherwise, we can wrap it up for today. So for this assignment, like, I hope everyone will be able to do all the questions because this involves just one single principle for ideal op-amp, right?
Yes, ma'am.
Okay. So does anyone has any other question? If not, then we can stop it for today.
Okay, madam. Thank you.
Okay. Thank you
Thank
for
you, ma'am.
attending. We'll meet in the next interaction.